Hi everyone. Yeah, my name is Victoria. So I'm a researcher in the Environment Centre and also the School of Computing and Communications here at Lancaster. And I'm from an environmental science background, and today I'm going to talk about soils and the human impacts on soils over the last sort of few hundred years. And my research is really looking at how we can use models and data science to help us understand or further environmental understanding, and in this case, how we can understand how humans have impacted soils and ensure their sustainable use going into the future. So first of all, soils are critical to life on Earth. Franklin Roosevelt, the former US president, said, "The nation that destroys its soil destroys itself." And this was in response to the 1930s Dust Bowl events that were a result of unsustainable agricultural land management practices and some extreme weather events. And the recognition there was that obviously these events were going to have severe effects on food production, which is obviously probably what we associate with soils the most. But actually, soils provide a whole host of benefits in addition to food production that are sometimes overlooked. So obviously, yes, in food production, soils provide around 95% of our food, either directly or indirectly. But they also support a range of biodiversity. So obviously above ground biodiversity, but even just the below ground biodiversity in soils accounts for about 25% of Earth's biodiversity. Soils are also important in regulating our climate. When we think of climate change and carbon sequestration, we often think of things like planting trees, but soils are actually the largest store of organic carbon in our Earth system, and they're actually larger store of carbon in our soils than in all the plants in the atmosphere combined. So they have a huge role to play in regulating our climate. Soils are also important for water regulation. In the storage of water within soils, they can provide resilience to both flood and drought events. And also soils can filter contaminants and pollutants and therefore can improve or regulate our water quality. Despite their importance though, unfortunately, soils globally are under threat, and the Food and Agricultural Organization estimates that around a third of soils globally are classified as moderately or severely degraded. And every year, that increases. So this is an ongoing problem. And just to kind of put a magnitude of that in your minds, it's estimated that around 500 million hectares of this severely degraded land is already completely abandoned. And that's larger than the size of the country of India. So some of the issues we see associated with soil degradation in the UK include things like compaction, so where we have heavy machinery and it compacts or squishes down the soil and completely changes the physical structure and functioning of the soil system. We also see issues like erosion, where we remove the natural vegetation cover on our soils, we expose the soils to erosive elements of wind and rainfall, and we can lose that soil far faster than it's generated. So some of the reasons that we see soil change, it's primarily really due to population growth. You know, since the 1800s, we've had a 7-fold increase in global populations, and associated with that global population increase, there's a huge increase in food demand. So because of that, there's been an expansion of agricultural land, which has involved the clearing of natural vegetation and removal of forest, which can lead to some of these issues that I've mentioned. But it's not just the changing of land use to agriculture, but also the intensification of agricultural management practices to meet this ever-growing demand for food. Soils have also changed due to atmospheric deposition of pollutants. So when we burn fossil fuels, obviously we release carbon into the atmosphere, but there's also a range of other pollutants like nitrogen and sulfur that are released into the atmosphere, which can be deposited on land through rainfall, which can lead to things like acidification of our soils and a change of the chemical composition. And climate change also can change our soils through changing or shifting temperature and precipitation regimes, which can alter the fundamental processes that operate within our soils. So the implications of soil change, because of all the benefits that we get from soils, they're wide-ranging but difficult to estimate. But the important thing to note is that soils can be lost or degraded far faster than they can form. So some of the soils in the UK, you know, hundreds to thousands of years old. So when we degrade these soils at a far faster rate, that we can't recover them really even within a human lifespan. So this is a really urgent problem. And while some studies have tried to put an economic cost on soil degradation, it can be difficult to do this because whilst not immediately obvious, but a lot of businesses depend on soils indirectly. So any supply chain that involves food or fibres ultimately depends on soils. And as we degrade those soils, it reduces the ability of those soils to function and ultimately can impact on business. So there's a real need to understand the complex system that is soils and understand how that they can respond to all these multiple drivers if we are to have effective policy and management of soils that can ensure the long-term sustainability of these systems. So how do we understand soil change? Well, primarily we do this through observations. And this has been done through local monitoring or a range of long-term agricultural experiments. We have in the UK, the Rothamsted experiments in the south of England, which can provide us with a wealth of data. And also national surveys. In the UK, we have the countryside survey data, which is hosted by the UK Centre for Ecology and Hydrology. And these observations are great in helping us understand fundamental soil processes and how soils can respond to different changes in drivers. But ultimately, observations are always going to be limited, both spatially and temporally in their coverage. And it can be difficult when we have all these different influencing factors on soils to disentangle exactly what's going on. And this is where environmental models can come into play. So models are essentially simplified representations of reality, and they're built on our sort of fundamental process understanding that we would get from observations. And they can be really useful in helping us understand complex systems like soils and complement the empirical or observational evidence that we have. And another key aspect of models is that we can use them to forecast into the future to understand what might happen under certain scenarios and understand the risk and resilience of these kinds of systems and ultimately inform the management. So this is what we've been doing in our research at Lancaster. We've been using a model called N14CP, which is a biogeochemical model. So it simulates the cycling of nutrients in carbon, nitrogen, and phosphorus. So the model simulates both natural land uses like forests and heathlands and bogs, and also agricultural land uses, a range of different crop types and rotations, and improved grasslands and grazing. It's driven by climate data, so temperature and precipitation, uses other readily available input data, things like the geology, the land use and the management history, and the deposition of nitrogen and sulfur, like I mentioned previously. So ultimately, the model simulates plant growth, simulates photosynthesis and the accumulation of biomass. And then as that plant material dies, it simulates litter production into the soil system, and then decomposition and a range of other soil processes. The model ultimately provides us with an estimation of the changes in stocks in both the plant and soil system of carbon and nitrogen and phosphorus. So how do we know that the models are doing anything realistic is often a question I get asked. So this is really where data is essential. So we can use data from some of those sites and agricultural experiments and national surveys that I mentioned previously to help us understand if the model is working and how we validate the model. So with N14CP, we've done this at both a local scale or site scale and also at a national scale. So for natural land uses, the model was compared to 88 sites across Northern Europe. And for agricultural land uses, we took data from 12 long-term experimental sites, but within those sites, there was various different plots with different agricultural management practices. So we could validate then the spatial performance of the model, and in the agricultural land uses, we could also look at the temporal performance of the model over time. We've also, in the national scale, we've compared the model to countryside survey data and also other national data sets like the Landis National Soil Inventory that's hosted by Cranfield University in the UK. And so we compare the model in these situations to observations of soil carbon, nitrogen and phosphorus, plant productivity, and also crop yields. So how much have soils changed in the UK? So this is one of the things that we've been looking at recently and understanding how much soils in the UK have changed since the pre-industrial era. So we've looked at how soils have changed since 1700 to present day, with the Industrial Revolution taking place in around 1800, 1850. And over this time, we actually see an increase in soil carbon of 13%, which you might think goes against what I just said earlier about soil degradation and how we might lose carbon from soils as we move to agricultural practices. But what's going on is a bit more complicated. So I mentioned about that atmospheric nitrogen deposition. And what we see is in natural land uses like forests, this nitrogen deposition acts a bit like a fertilizer. And the reason that happens is because plant productivity in natural systems is predominantly in the UK limited by nitrogen availability. So we add this nitrogen, it enhances plant growth, which enhances litter production into the soils and increases the soil stores. But at the same time, whilst we see an overall increase in the UK, it's highly spatially variable. And obviously, since 1700, we've had massive agricultural expansion in the UK, particularly in arable expansion in the east of England, you can see in this figure. And in those areas, we see dramatic losses of soil carbon over this time. So whilst a 13% increase might sound like a good thing, actually, it's perhaps not. And it's unlikely that this kind of increase in soil carbon will continue as we go into the future. And there's several reasons for this. So the first one is that this nitrogen deposition would need to continue if we wanted to keep that soil sequestered in the natural land uses that we've seen. Now, that's not really a good thing because this nitrogen deposition ultimately comes from pollution and burning fossil fuels, which has other issues, but actually nitrogen deposition is also associated with a range of other negative effects like water quality issues and loss of biodiversity. So we don't really want to keep doing that. The other issue is that even if we were to continue depositing nitrogen on these systems, they might not continue to enhance soil carbon. And the reason for this is that whilst at the moment we see this increase because those plants are limited by nitrogen availability, if we keep adding nitrogen, they might become limited by something else, like another nutrient availability or water availability. But the other important thing to note is where we've lost soil carbon in these arable systems, they're actually still losing soil carbon. And 13% gain might sound like a lot, but it wouldn't take much for this to shift in the other direction. So if we stop gaining soil carbon in natural systems or even start losing some of that soil carbon, we could quickly change this gain into a loss. And the other thing is, if we compare this 13% increase in topsoil carbon to emissions across the UK over the same period, it's less than 1% of UK emissions over this period alone. So it's, in terms of climate mitigation, it's not really a happy story. So that's the work we've been doing so far with our model. And some of the other work I'm doing is looking at how we can use digital technologies and to helping further our environmental understanding. And really, we're in an exciting time because we've recently, over the last few decades, experienced a step change in the availability of this kind of data that we can use to build these models through the getting satellite information and remote sensing. And this whole range of large data needs analysing and interrogating and understanding. And data science and advanced statistics and machine learning methods can provide exciting new ways which we can explore this data and find new patterns and help find new understanding within environmental science. So I think there's a real role for the mutual working of the process-based models like N14CP and data-driven models taking advantage of this big data. And another thing that we've been looking at is the role of cloud computing for collaboration, but also when looking at these models and understanding complex systems like soils, cloud computing provides us with greater processing power and allows us to bring researchers from anywhere in the world together. So it helps us promote this systems thinking framework. So in summary, soils provide a range of benefits to society, and not just food, which is what we'd often think of, but also water, climate and biodiversity. But we've changed soils significantly due to human influence. Unfortunately, this has resulted in a lot of degradation issues. But our research is looking at using data and environmental models together to help us understand these systems and understand risk and resilience and promote sustainable management practices.